My expertise is really in river restoration, fluvial geomorphology, and engineering of rivers. But I have some experience with bluffs and ravines as well, and so I've been involved a lot with a lot of these workshops and meetings here in the valley, and so I'm going to talk a little bit about first the factors that influence gullying and ravine formation and what goes into stabilizing those, and then talk about some technical examples I'll show you, and then I'll briefly run through the outcome of the workshop that we had back in 2011. So this talk is a modification of one I gave a couple of years ago, actually in the same room, for mostly agency people, but I've added a few things. First, just want to throw a couple of definitions out there that I'll probably use a lot. Hydrology versus hydraulics. We call these H&H when we're designing things, but hydrology is really how much water is coming down. So how much flow is in the stream. And that's related to, of course, rainfall frequencies, snow melt, groundwater, and stream flow. Hydraulics is really what the water is doing once it's in the channel. Turbulence, erosive power, ponding, backwater, things like that, eddies. Patrick really talked about this stuff in some detail, so I'm not going to really talk about it much at all. Just to say that all of these things really influence ravine formation and bluff erosion. What we'll be mainly focusing on are the bottom two there, flow in the once it's in the ravine, and then shear stress, which I'll talk about later. It's important to talk about rivers in terms of the age of the river, the water body. So if you want to look at it this way, headwaters are much younger. So post-glaciation, once the glaciers have retreated, these streams start to form. Older streams at the bottom of the watershed are lower gradient, much more tortuously meandering, like the Minnesota River, for instance. This is a couple of mountain examples, but higher up in the watershed you have much deeper streams. In the middle you've got the sort of gravel, riffle, cool, meandering streams. And then at the bottom again, the really highly meandering systems with very, very low gradient. And generally we look at the younger streams as the sediment source areas, so the upstream areas where the sediment's coming from. Around here it's actually kind of in the middle where you're getting a lot of the sediment. And then at the bottom is sediment sink where the sediment is dropping out. This is just another picture of that. Headwaters are where we have the active gullying ravine formation going on. Lower valleys where all that sediment ends up. This is a channel evolution model by a guy by the name of Stan Shum. But what he tried to show here, both over time and in space, is how rivers evolve when they have disturbance. So on the top left there, you've got a stable stream. And we introduced some change there, either the base level of the Minnesota River drops, for instance, or we start pumping more water or releasing more water into the stream quicker. Usually what happens is incision. And so the first thing that happens is stage 2 of the model is this downcutting. Once that reaches sort of an equilibrium, you start to get widening. And then a lot of times these streams will stabilize again later at a lower elevation. And if you were to look at the stream in cross-section, that's the top row. If you kind of unzip the river down all the way and look at it from the side, you'll see that in the upper part of the watershed is where you get these nick points, or waterfalls, if you want to call them that, head cuts we call them. All translating, moving their way upstream. What we're primarily focused on here is the stage 2 and 3 of the model, where we're getting incisioning, ravine formation, and widening, which also applies to the bluff erosion chute. So a lot of times, before we do anything, we want to ask, do we really need to do anything at all here? And I think we all do this in our head, not always calculating things, but some sort of risk assessment, a cost versus benefit analysis of what we're doing. So what's the risk of leaving something to its own devices, or should we do something? The risk is often talked about in terms of the probability of the occurrence. And these examples just say 50%. There's a 50% chance of you losing acreage, and then times the cost of losing that acreage, divided by the number of years of interest. And you can do a lot of research into this and calculation, but oftentimes it comes down to just a judgment call for private landowners. First I'll talk about passive or hydrologic treatment, so treating the water before it actually gets to the channel. Sometimes you don't want to do anything at all after you do that risk assessment or make a judgment call there. Maybe the best thing to do is just work with folks like Patrick and all the county folks and state people in trying to figure out really what's this ravine doing, where is it going, and maybe monitor it and see if I really need to do anything. And then kind of the opposite approach is then to actually move the asset away from the problem and just let nature take its course. That's easier to do with roads and bridges, a little harder to do with structures. And of course, crops and pasture are not necessarily movable assets, so we really can't move those. So then we need to talk about modifying the amount of water coming into the channel. Prior to agriculture, at some point, certainly there were fire and other management of these ecosystems by natives, but when you had forested ecosystems or prairie ecosystems that were undisturbed, they were much better at absorbing water and getting it down into the ground, and then that would meter the flow out a little bit longer. We had a lot more perennial streams back then, streams that flowed all year. And they looked, both the ephemeral and perennial streams look more like these do. They're stable, banks are stable, they're not down cutting, and not a lot of change over time. When humans get involved, doesn't matter what we seem to do, the same result almost always happens. This is a graph called a hydrograph of stream flow on the left versus time during a precipitation event. And so when it rains, say on the left side of the graph, in the dotted line, before there's a lot of disturbance, that water took a lot longer to get to the creek and it metered out slowly. Now we've created a much more sharper hydrograph where the water is hitting the stream faster, it's warmer, and the peaks are higher. There's much more flow going in a shorter amount of time. Why is that bad? Well, because you've taken what may have been a formerly stable swale or drainage, turn it into an active channel that really gets more and more flow as it incisors, concentrating into that space. And so as the channel gets deeper, the whole problem gets worse, because now instead of water out on this swale or floodplain area, it's all concentrated in this canyon basically. And this on the right here, this picture near Rochester, that happened over the course of about 10 years. So it can happen very rapidly. The red line here represents maybe a target that we can get to. We probably can't get to pre-development or pre-ag kind of curve, but we have been able to get somewhere in between, some happy medium perhaps. Makes stabilizing our ravines easier then. One of the things that we can do, of course, is to create wetlands or to restore wetlands in the headwater areas. Wetlands are better at storing water, infiltrating it, getting it down into the ground. These two pictures here are of the Swamico River, South Branch, and Oneida, on the Oneida Nation property, where they just really created a few berms, bermed up the water, detained it a little bit, slow it down. And there are obvious habitat benefits there too. Lost cobs, we talk a lot about those in the workshops that we've had around here. Water and sediment control basins, I'm sure a lot of you have these on your property already, but berms and small detention basins. There are a lot of standard designs out there. NRCS has standard practice designs for these. And we'll talk about these later today, I'm sure, in some detail. They vary in size. They can be narrower berms if you have pretty flat land, or bigger, wider berms if it's steeper, or if you want to work the surfaces with farm equipment, for instance. Occasionally, particularly in urban areas, we can catch water in catch basins, drop it down in a pipe, and have that pipe pop out lower down in the watershed somewhere where it's going to do less damage. Buffer is another way of slowing down the water as it gets to the ravines. For these to really be effective, though, you need a lot of buffer width, and that's, of course, every foot that you take out is another row of whatever you're planting, so that there's a cost benefit there as well. So first I want to talk about treatments for this stage 2, the incision, or down cutting. Stiff grass treatments, there's been some research on these. I don't know that a lot of this is being done around here, but this is really getting at swales before they become an active channel. And so you're putting rows of switchgrass and other plants in and amongst just the regular vegetation that's in there to try and create just mini check dams, or what we call roughness, to slow the water down and prevent it from forming rills, which lead to gullies, which lead to ravines. A lot of this has been done, a lot of the research work on this has been done in Africa and India. As we get more toward more robust treatments, we need to talk a little bit about when should I use things like rock versus vegetative stabilization. So bioengineering really uses plants to stabilize the soil. So the questions we'll talk about as we go along here are, what is bioengineering? When is that appropriate versus more robust treatments like riprap, for instance? When can we use it? When do we get into more geotechnical stabilizations? I'll talk about what that means in a minute. Once the water is in the channel, what we're really talking about is this equation here, which is shear stress, which is this tau on the left side, is really a product of the depth of the water and the slope. So the steeper your channel is and the deeper the water is, the more erosive power that stream has. Makes sense. That's why a lot of our treatments for stabilizing banks are at the very toe, at the deepest part of the channel. So this is, looking at this picture here is the right side of a channel. The water's deeper on the bottom, right at the toe. That's where we put the treatment usually. Bioengineering combines sometimes harder treatments like riprap, in this case a riprap toe, versus bioengineering or green plant-based stabilization of the upper slope. And bioengineering solutions generally get stronger over time, whereas a lot of our structural stuff that we put in the creek just falls apart and gets less stable over time. So when can we use bioengineering? Any material will move given the right amount of flow, right? The right depth and slope. So I was just out in Colorado last week, looked at some canyons there, and after the Colorado floods in October, and there were 5-foot boulders that were tumbling down these canyons like they were pebbles. But in other places, you don't have enough energy to move sand. And so it really depends on that shear stress equation that we talked about. Bioengineering solutions, generally when you're under about a pound and a half of shear. So shear is a force, and so we talk about it in terms of pounds per square foot. So under a pound and a half of shear, we can use bioengineering solutions. Compare that to, just to kind of give you an idea what that means, how much force can your design withstand? Well, typical straw mat can handle about 1.4 pounds of shear right when it's put in the ground. They use that a lot on roadside slopes. Different types of vegetation you can see right around in that 0.4 to 1.5. There's a couple of more robust treatments that are higher. And then your riprap, 6 to 12 inch riprap, you're up into 2 to 4 pounds per square foot of shear. So that gives you kind of an idea of what we're talking about here. Other times, there's more at work than just the water moving the dirt around. Gravity plays a big part in bluff erosion, especially, and ravine erosion. So if you start to undermine the toe of these big slopes or these ravines, you just have so much weight on top, pushing everything down. It's just got to collapse. We know this has been in the news big time with the stuff out in Washington. Can lead to pretty tragic consequences. And as Patrick showed, it contributes a lot of sediment to the river. Excuse me. So traditionally, back in the CCC crew days, they put in a lot of check dams all over the place to try and stop head cutting or nick point movement upstream. Wood, of course, doesn't last very long, and so those are ephemeral kinds of treatments. Some of the stone stuff, like this one on the bottom right in Rochester, is still there. It looks great. It doesn't show any signs of degradation whatsoever. Other things are meant to be more temporary, or on the bottom left, more permanent. The sheet pile check dams are used pretty frequently. Folks out in western Iowa, the Hungry Canyons people, they have a lot of ravine erosion out there. Here's a picture of both of these of a sheet pile check dam that's got riprap on the front end of it. Gives it added stability, keeps it from cantilevering forward, and it can also allow for fish passage if they're done correctly. Stone weirs or rock weirs can be used as long as they're put in properly. The one on the right is about a 10% slope, so they can be used in pretty steep environments. What are these things doing? Well, check dams are really, what you're doing is imposing artificial geologic control. So here's a picture of Amnicon Falls State Park in Wisconsin. Bedrock controls everywhere, steps going up. We're just putting that in place. But one thing you notice about the bedrock here, that it goes all over the place. It goes far beyond the edge of the stream. The main problem with check dams is that we don't do that a lot of times. We'll just put the dam in the channel and not embed it into the sides of the valley wall. And that's the most common source of failure, is flanking around the outside. If you don't, like if you're driving sheet pile, for instance, and you don't drive it deep enough, you can get water pressure that will eventually push water out through the bottom and seepage around the sides, and then that can cause your structure to fail. Scour over the top. A lot of people will put a check dam in and not worry about what's downstream of the check dam. And so when water comes down during the flood, spills over, digs out of the bottom hole there, and the whole thing falls in, collapses, especially stone check dams or rock weirs, for instance. Sinking, so if your soils aren't solid and you put a check dam in, it can just eventually winnow out, find sediment below it, and just sink down through into the ground. You see that a lot with ditch checks that are put in with big heavy riprap, and they don't use any smaller material in the middle of it. You'll get winnowing out of underneath, and the whole thing just sinks down and doesn't do any good. India's done a lot of work with gully erosion and ravine formation, and really a lot of the solutions that we have now haven't really changed since the 1940s or 50s. There was a lot of work done by the Forest Service out west in the 30s as well, and really the stuff that they came up with then still applies. And what both of those groups found is that when private landowners a lot of times try and do a check dam themselves, it works for a little while, but if it doesn't have any engineering or any consultation associated with it, there's a high degree of failure on those. And that also applies to construction oversight. So it helps to have somebody helping you out with those designs. Other things that we can do, we can build more natural looking kinds of drop structures. The top right is a project out in Massachusetts. And this is an 8% slope step pool channel using boulders basically. The bottom left is in Milwaukee. It's a 2% slope. This is a riffle pool channel. Just a constructed riffle there to stop any head cutting from going upstream and exposing a pipe that's just upstream of that riffle. When you're in the 3 to 6% slope range, you can do things called steep riffles. These are a couple of different examples of that to stop active ravine erosion over in Olmsted County. Just another example of, this is that same Rochester project I showed you before, but steep riffles. This creek is dry 99% of the time, but it gets really big flows every once in a while. You can also, if you have a widespread incision that's, maybe that creek like this one on the top used to be very small. The landowner here, this is Pica Creek by Pica Cabinets on 169. The owner there, Jay, used to be able to jump across this when he was a little kid. He said it was about 2 feet deep, maybe 4 feet wide. But land use changes, hydrology, climate, all that stuff went into making this thing cut down, and pretty soon you had a 12-foot deep channel. And the solution here, since the head cut had not really translated its way up into the bluff, into the steeper areas, we raised the channel up and created more of a steep riffle pool channel through there. So at some point then, either you're in a ravine and you have this widening starting, or you're on the main river like Patrick showed and you're getting bluff erosion. So what is bluff erosion? Just a quick definition. Stream bank erosion is when you have erosion on the floodplain area. So in the middle there, in the light colored, where it says active channel, your stream is abutting against the active floodplain. So the floodplain, the river can move around in there pretty actively. Where the stream goes to the far left or the far right here, it abuts against an older geologic surface, an older terrace, which is actually an older floodplain that's been abandoned now. That's where we have bluff erosion. Those are generally bigger, 10, 15, 30, 100 feet high. And that's where a lot of our sediment's coming out. We saw a lot of sediment in the Minnesota River Valley comes from bluffs. Up in northern Wisconsin, we're talking 90% of the sediment in some of those watersheds is from bluff erosion. So the simplest thing we can do, you see a lot of this done, but rip-wrap the toe, that can work, especially if you couple that with some bioengineering treatment of the upper slope. The biggest problems with riprap is that in river systems, you disconnect the upper slope from the river. And so if you're a frog or a salamander and you want to get up there, you can't. Or if you're a turtle and you want to nest up there, you can't get there. And so it may not, and also may not impact the geotechnical solution. So you may put riprap there, but you still haven't solved the gravity problem. And so you may need to do something else. Like here, for instance, where we're just doing simple grading. So this is, there's a zoo on the other side of this bluff, and they didn't want the zoo to fall into the river, and so we really just did a rock toe there, graded the bank back at a cost of a couple $100,000. It costs a lot of money to move that much material, and did some native plantings there. And so gravity was the real big enemy here, combined with the erosion at the toe. And so just a few years later, it looks like that. Pretty simple. This is in Prior Lake. This is a steeper channel, so this is about a 3.5% slope stream. Boulder, or not a boulder, but a small, large cobble bed channel. So we essentially just built a little toe, and the stream used to be right up against the toe of that bluff on the left side. We just moved the channel over. Built a little bench there and a rock toe on the bottom. Also very simple solution. Extending the toe out from these bluffs is something that can be done with rock or a combination of bioengineering kind of treatments. This is Porter Creek up by New Prague, where we pull the toe out away from the bluff with an engineered log jam, we call it. This creek, although very small, gets some pretty big floods, and so we had to build kind of a beefy structure. It's really just driven logs, piles. You can see the vertical piles there, and then logs mixed in there, Some of it's actually cabled together, and then you're backfilling it with material that you're digging out to move the channel over. So we're essentially just digging a new channel, throwing that material back into the logjam, packing it down, and not doing anything to the upper bluff slope. So to grade a big bluff like that costs a lot of money. This 100-foot section cost, I don't know, we can ask Paul, I forget how much it costs, but you can do many, many more of these than you could for the cost of grading a big slope like that. And it immediately starts to vegetate, and then the vegetation creeps up the slope. You don't really need to do anything to that upper slope necessarily. You had asked a question about layers of sediment and how that plays in. Bluffs can come apart much more easily if they have a layer of clay, say, and then a layer of sand and clay, or maybe you've got sand on top of clay, and so the water goes into the sand, infiltrates down just fine, but then it comes out right at the interface between the clay and the sand. And that can cause slopes to fail. And also, if you're constantly winnowing or entraining sediment away from the toe of these bluffs, they're never going to stabilize because they just keep sliding in. And so this is a way of kind of stopping that process. That's just the same place looking at it from the top down. Here's another one, same kind of concept. This is a little bit lower profile bench, but just moving the channel away from the toe and stopping that toe erosion from happening. You can also do much more active stabilization of those slopes. Here we have two examples where we had pretty big expensive infrastructure on top of the hill. The Little Miami River was a project that we did back in the mid-'80s where there was a big lake on the other side, and they didn't want the river to breach the lake, and so we rebuilt the slope using these stacked kind of honeycomb structures that fill with sediment. Scott County, and Paul Nelson can tell you more about this one, did a project to save a house that was on top of a bluff, and they used similar treatment there. And he can give you the details on that. This is a similar project, rock toe, those stacked geocells on the bottom, and then a graded slope on top. And that, here, remember we talked about shear stress, so bioengineering can handle about 1.5 pounds of shear. This had about 10 to 14 pounds of shear stress on the toe, and that decreased pretty rapidly as you went up the slope. Terracing, again, just in a way of getting rid of the gravitational problem, so removing weight from the top of the slope, so you can, this is in New York, but you can kind of terrace that up, and then you're really only worried about the gravity that's acting just on that one level. You can encapsulate soils. Here we're using, again, a rock toe in one spot of this bank and then a wood toe in another. This is out in Portland, Oregon. And then on top of that, you've got encapsulated soil, so soil that's encapsulated in fabrics, biodegradable fabrics that will break down over time. And but in the meantime, then the vegetation grows up and stabilizes the soil. Again, here we had really high shear stress at the bottom of the slope at the toe, but that rapidly decreased as we went up and allowed us to do the bioengineering on the upper part of the slope. Sometimes you want to, if you have a really big slope, you want to stop rill erosion from going down and creating a gully within your bluff. And so you can use things like willow wattles, or in this case, on the Mississippi River, we just used straw wattles every 6 feet along the face of that slope. This is actually a boat wake erosion problem and not a riverine erosion problem. But so just a couple more slides. What I want to talk about is just a recap of the 2011, well, it's 3 years ago now, the workshop that we had here, a ravine stabilization design charrette meeting. A lot of the people that are in the room here were part of this. I was just a small cog in this wheel, but we looked at a variety of different treatments, and we ended up kind of separating things into hydrologic treatments and the hydraulic treatments, which is what I did today too. And I showed you all of the things that we talked about, but the preferred options were things like enhanced or restored wetlands and these waskouts. Fairly cheap and easy things to do. Things that were less popular were newly constructed wetlands and then also buffers. That's a no-brainer, I guess. We're trying to farm the area. Buffers are generally not as popular. And then the primary hydraulic modifications favored were the soil and biotechnical engineering solutions that we talked about. Inlet control, so controlling erosion at where the tile drains come in, and then the grade controls that we talked about there. Less popular, but still in the mix, are bed and bank armoring, some of those more intense plastic-based geosynthetic solutions I showed you, and then the large wood, engineered wood. Not recommended were gabions. The gabion baskets, these chain link fence things that are, you put rocks in them and sew them up, and you can use those on slopes. Well, those were developed for mountain areas up in the Dolomites in northern Italy where they couldn't get heavy machinery. And there's no water up there, and it's extremely dry. So, but you see a lot of gabion-based stuff around here in the water, and it has no place there because it's going to last about 10 to 15 years, and then it's going to start becoming a sort of a time-release delivery system for cobbles. And then the whole thing's going to fall apart. So if anybody tries to sell you a gabion product, just say thank you, no. And then some of the vegetative options, again, were the stiff grass treatments, thinning of forest canopies sometimes, and then control of invasive species, buckthorn, etc. And that's all I've got. So how did I do on time? Do we have questions? Time for questions? Okay.
The buckthorn is about all that grows on my ravine.
Yeah.
Do you recommend cutting it, or just trees above it, so that the shade there?
Yeah, so the question was, buckthorn is by far the most popular plant in his ravine. Should he cut that down or what? And that's a tough one because you can cut buckthorn down and treat it, but unless you keep doing that and keep spraying it constantly, it's going to come back. There was a study done recently by a grad student at Wisconsin, I think, or Minnesota, where they looked at buckthorn treated areas and that have been treated for several years with spraying and treatment of stumps, etc. And as soon as they backed off of there, within a couple of years, you have more buckthorn coming up. So this is not just a problem with buckthorn. It's a problem. It's really the bane of river restoration is an invasive species. And all of you have farms, so you have reed canary grass everywhere probably. That didn't exist 100 years ago. It's a European species, and so all these plants have replaced our native plants. And the point about getting rid of them is that having a more diverse canopy of different plants and shrubs and things like that holds the soil better than some of these invasives do. If you're prepared to take on the buckthorn and keep at it and invest the time, you can do it. Otherwise, it's really maybe selective management of it is the best thing. I don't know. My dad's got the same problem at his house too, so I don't have a good answer, I guess.